Welcome to chapter 6. So in this lecture we'll talk about thermochemistry and the energy flow and chemical change. So in this lecture, in this chapter, we'll discuss what are the forms of energy and their interconversion, what is enthalpy and the chemical change at constant temperature. We'll talk about calorimetry and how to measure the heat of a chemical or a physical change. And number 4, we'll talk about stoichiometry of thermochemical equations. Number 5, we'll talk about Hess's law. And finally, we'll end with the standard enthalpies of reactions. So let's talk about thermodynamics. So thermodynamics is the study of energy and its interactions. So what forms of energy that it happens, and it mostly deals with heat and its interactions with the surroundings. So thermochemistry is the branch of thermodynamics that deals with the heat involved in chemical and physical changes. So thermochemistry is the part of thermodynamics that only deals with whether you have heat involved in whenever you have chemical and physical changes. So when energy is transferred from one object to the other, it appears either as work or heat. In physics, mostly it occurs as work. In chemistry, it comes out as heat. So what we call a chemical system. The system in this reaction, in the picture that you see here, is the contents in the reaction flask. Everything around that particular reaction flask will become the surroundings, even the flask by itself. So the only reactants that are inside that particular flask become the main substituents. Everything else becomes the surroundings. Now, a meaningful study of any transfer of energy requires the understanding of system and its surroundings. So whenever we have combined system and surroundings, we call that the entire universe. So system plus surroundings is the universe. Now, the total internal energy of a system is the sum of potential and kinetic energies of all the particles that are present in that system. Now, the total energy of the universe will always remain constant, but the only thing that changes is the interactions of energy between surroundings and the system. So sometimes there might be system losing energy. That loss of energy is added into the surroundings. Sometimes the energy is being taken from the surroundings and put it into the system. So a change in the energy of the system must be accompanied by an equal and opposite change in the energy of the surroundings. So whenever you have a reaction where you start at a higher energy and the final state has a lower energy, so if the final state has lesser energy than the initial state, then we call that the energy being released to the surroundings. So that net energy that is lost will go into the surroundings. Now, there are some cases where you might start at a low energy and you might have to end up with a high energy in the final state. This is where the energy is being absorbed from the surroundings. So the net energy change is always taken as the final energy minus the initial energy. This, in terms of chemistry, is written as the product energy minus the reactant energy. Now, the same thing happens when you have heat as well. When you have a hot body cooling down, the energy released goes into the surroundings as heat. When a general body undergoes cooling, then it has to absorb energy from the surroundings. For it to become from ice to room temperature water, it is absorbing energy from the surroundings to become room temperature water. The same thing happens with work as well. So when you have a system that's undergoing compression, when you have a free system undergoing a compression, it does work by the system, work is done by the system. Now, when the system is undergoing an expansion, then the work is done on the system by the surroundings. So these are the energy differences that you will see. The common sign conventions that are used is we use Q to be positive when it gains heat, meaning that the system is releasing the heat. Now, for W, positive means the work is done on the system and negative means that the work is done by the system. So when a system releases heat, it becomes positive. When the system gains heat, absorbs heat, we call it positive. When the system releases heat, it becomes negative. Work done on the system is positive. Work done by the system is negative. So these are the differences that we generally see here. Now, let's talk about the law of energy conversion, which is also the first law of thermodynamics. So the first law of thermodynamics basically states that the total energy of the universe is always constant, which means that the energy is conserved and it is neither created nor destroyed. So we cannot create energy, we cannot destroy energy. but it only changes its form from one form to another form. So it only changes its state from one form to the other form. So the total energy of the universe is the sum of the energy of the system plus the energy of the surroundings, and the total change in the energy of the universe is always equal to 0. Remember that there is no change in the total energy of the universe, it always stays constant. So the only thing that changes is either the system energy or the surrounding energy. Now what are the units of energy? The common unit of energy, or the SI unit, is joule, which is 1 kilogram meter per minute square per second square. But in terms of chemistry, we use a unit called calorie. So calorie is basically defined as the quantity of energy needed to raise the temperature of 1 gram of water by 1 degree centigrade. So 1 calorie equals 4.184 joule. The other common unit that is used in the US is BTU, British Thermal Unit. It is often used to rate appliances. Most commonly you would see this in air conditioning equipment or heating equipment. So BTU here is equal to about 1000 joules. So that's about 1055 joules. So 1 BTU is about 1055 joules. For example, if you take your air conditioning, and if it says that it's a capacity of 7000 BTU, it means that that is the amount of heat that it can take out in a certain period of time. Now, these are some general quantities of energy. For example, average kinetic energy of a molecule is about 10 power negative 21 joule. The daily solar energy output is about 10 power 24 joules. So these are some energy differences. So let's take an example and let's solve a problem. So here what is given? So when gasoline burns in a car engine, the heat released causes the product CO2 and H2O to expand, which pushes the piston outward. So we remember that here the piston is being pushed outward, where the system does work on the surroundings. So work is done by the system. So excess heat is removed by the car's radiator if the expanding gases do 451 joules of work on the pistons, and the system releases 325 joules of energy to the surroundings as heat. So Q here is releasing heat, which means that it's negative 325 joule, and the work done W is also negative because the work is done on the system, work done by the system, so minus 451 joule. So they are asking us to calculate delta E. So from the Newton's first law of thermodynamics, we know that Q plus W equals delta E. So delta E can be calculated as minus 325 plus minus 451. So when you add up the total value, so that total value becomes minus 776 joule. But they are asking you for in joule, so this is minus 776 joule. Now they are asking you in kilojoule. Kilojoule is 1000 joule, so divide the entire value by 1000. So delta E becomes minus 776 by 1000 kilojoule, so which becomes minus 0.776 kilojoule. In terms of kilocalories, so divide the entire value by 4.184. So delta E becomes minus 0.776 by 4.184 kilocalories. So when you substitute the value, you get 0.776 over 4.184. So that becomes 0.185 kilocalories. So negative 0.185 kilocalories. So this is how you can convert from one unit to the other units. Next, let's talk about enthalpy. So enthalpy here is basically a form of energy. So we know that delta E is Q plus W, but the most common form of chemical work is what we call the PV work. PV work, the pressure volume work. So the work done here is when the volume of the system changes in the presence of an external pressure. So the change in the volume in presence of an external pressure multiplies, gets you the value for enthalpy. Enthalpy can be taken as E plus PV. So we are basically converting W into PV. So delta H becomes delta E plus PV. So if the system has a constant pressure and there is no change in its volume, then delta E becomes nearly equal to delta H. So whenever you have, for example, there are two ways in which energy is released. If you take the same pathways, there are two different pathways for energy change. When you burn fuel directly, it releases directly as heat. But the same fuel in a car, some part of it is released as work, and which drives the car forward, and some part of it is released as heat in the form of exhaust. So this is the difference here. So what is the pressure volume work done? So initially you have a volume V1 and you're changing the volume to V2. So the work done here is given as, so we have the same pressure minus P times delta V. Notice that the work done is on the system, so it is negative here. So work is done by the system, sorry. Now delta H here is the heat of the system at constant pressure. So QP becomes equals to delta H. So delta H is nearly equal to delta E, provided that the gases do not involve gases. It does not involve gases, and in which the total amount of moles of gas does not change. And the last point is for reactions where QP is much larger than P delta V, even if the total number of moles will not change. So these are some conditions where we can consider the enthalpy to be nearly equal to the energy change. So these are examples. So there are two types of processes based on the enthalpies. If the net enthalpy is negative, so if delta H is less than 0, then it releases the heat out of the system to the surroundings. We call that an exothermic process. So in an endothermic, the other one is an endothermic process where it absorbs energy from the surroundings into the system. So here it releases the heat to the surroundings, here it absorbs the energy from the surroundings. So let's take an example here of a problem here. So a reaction taking place in a container with a piston cylinder assembly at constant pressure produces a gas, and the volume increases from 125 ml to 652 ml against an external pressure of 988 torr. Calculate the work in joule. So we know that the work done is minus P delta V. So they have given us V1 and V2. So V1 is 125 ml and V2 is 652 ml. Now convert it into liters, so it becomes 0.125 liter, 0.652 liter. So work done becomes minus P times V, delta V becomes V2 minus V1. So minus pressure here is 988 torr, converted into atmosphere, divided by, so 988 divided by 760 atmosphere. So when you calculate 988 divided by 760, that gives you 1.3 atmospheres. So 1.3 times V2 is 0.652 minus 0.125. So 0.652 minus 0.125 times 1.3. So that gives you a value of minus 0.6851. Remember that the unit is atmosphere liter, but in this they are already given 1 atmosphere liter is 101.5 joule. So minus 0.6851 times 101.5 joule. So that gives you a final answer of 69.54 joule. So the work done, W, is minus 69.54 joule. So next let's talk another problem here. So in each of the following cases, determine the sign of delta H and whether the reaction is exothermic or endothermic to draw an enthalpy diagram. So let's look at the first reaction. In the first reaction, both the reactants are mixing and they produce a product plus they release some energy. So remember that here, if the energy is on the product side, this energy, so if the energy here is on the product side, it means that this is releasing energy, releasing heat, so which means this is an exothermic process. In the second reaction, it first absorbs energy and takes in liquid form of water and converts to gas, so which means that here it's absorbing energy, so which means this is an endothermic process. So this is an endothermic process. So if the energy is on the reactant side, it means it's an endothermic process. If the energy is on the reactant side, the product side, it's an exothermic process. So this is the difference that we can use to judge. Next, let's talk about calorimetry. Calorimetry here is basically calculating the specific heat capacity of a substance. So what is specific heat capacity? Before we go into specific heat capacity, let's talk about the amount of heat that a body carries. So the amount of energy or the amount of heat that a body carries can be calculated as its specific heat capacity times mass times the temperature change. Now, what is the specific heat capacity here is it's the quantity of heat that you require to attain the temperature of 1 gram of a substance by 1 Kelvin. Now, Q here represents either heat lost or gained, C here represents the specific heat capacity, M here represents the mass in grams, and delta T represents the change in temperature, T final minus T initial. So these are some specific heat capacity values for different substances. Notice that water has one of the most highest specific heat capacities of many substances. That's the reason why water is used as a coolant in many cases, because it can take a lot of heat with less mass. So with smaller quantities of the substance, it can take a lot of heat. So that is the reason why we call this water is a really good coolant. So let's take an example here. So what is given in this problem? So a layer of copper welded to the bottom of a skillet weighs 125 grams. How much heat is needed to raise the temperature of the copper layer from 25 degrees to 300 degrees? And they have also given the specific heat capacity of copper as 0.387 joule per gram Kelvin. So write down all the data they have given. So C equals 0.387 joule per gram Kelvin. Mass is 125 grams. So they are changing the temperature from 25 degrees to 300. So T1 is 25 degrees. TI, let's call it initial TI. TF is 300 degrees. So 25 plus 273, which becomes 298 Kelvin. 300 plus 273 becomes 573 Kelvin. So always remember to change the temperatures into Kelvin. So they are asking you how much is the heat needed to raise the temperature. So Q, the formula is C times M times delta T. C here is 0.387 times M, which is 125, times delta T is TF minus TI. So remember the formula, TF final temperature minus initial temperature. Final temperature is 573 minus 298. So calculate the value. First calculate the difference, which is 573 minus 298, which becomes 275. So you have 0.387 times 125 times 275, and multiply that with 125 times 0.387. So that value becomes 13,303.125. So if you, this is in joule, if you want to write it in kilojoule, it becomes 13.303 kilojoule. So this is Q. So there are calorimeters that we use to measure this specific value. So calorimetry is the basis of finding this particular value of C. So the common ones that are used is, one of them is coffee cup calorimeter, so which involves an insulated outer layer of a cup inserted with a stirrer and a thermometer, and the sample that you want to have test its value for the specific heat is placed in a sample box and dumped into or placed inside the water, and it's filled with water, and the water is insulated. So here remember that the main principle is that the heat, so the main principle here is that the heat lost by the sample, by the body, is equal to the heat gained by water. So this is the principle that we use to represent here. So Q lost is equals to Q gain. So this is the principle that we use to represent the system. So let's take an example here. You have a 22.05 grams of solid is heated in a test tube to 100 degrees centigrade and added to 50 grams of water in a coffee cup calorimeter. The water temperature changes from 25.10 to 28.49. So find the specific heat capacity of the solid. So the Q of the sample is equal to the Q of the water. Remember that here one is losing the heat, the other is gaining the heat. So remember that the sign here is very important. So Qs is equal to minus Qw. Remember that gaining heat is negative, so we consider that minus Qw. So Qs can be written as mass of the solid times specific heat capacity of the solid by the temperature change of the solid is equal to minus the mass of water into the specific heat capacity of water into delta T of water. Now we are finding this value Cs. We already know Cw, the value is 4.184 joule per gram Kelvin. So Cw is 4.184 joule per gram Kelvin. So substitute all the values into the formula. Mass of the solid is 22.05. So 22.05 times Cs times delta Ts will be, we are changing it to test tube to 100 degrees. So you are heating to 100 degrees centigrade and adding it to the water. Remember that their final temperature will always be the same. Delta Ts here is going to be T initial minus T final, which means that when you are heating up it to 100 degrees and dropping it in water, the water initially, which was 25, will rise to 28.49, which means that both of them, the final temperature for both of them is 28.49. So you have 28.49 minus 100 is equal to minus the mass of water is 50 grams times Cw is 4.184. Here, because we are taking the difference, we do not need to consider the change in temperature also. So remember that you don't need to write it in Kelvin as well. You can change it into Kelvin, but that doesn't change your answer as well. So times the change in temperature of water is, this is the final temperature minus initial temperature. So 28.49 minus 25.10. So now Cs becomes minus 50 times 4.184 times 28.49 minus 25.1. So 28.49 minus 25.1, that becomes 3.39 divided by 22.05 times, you have 28.49 minus 100, the value becomes minus 71.51. So minus minus gone, and calculate the value. So you have 50 times 4.184 times 3.39 over 22.05 or 71.51. So the solids value is 0.4497. So we can write it as 0.450 joule per gram Kelvin. So this is the specific heat of the solid. So this is how we can calculate the specific heat of materials by using the coffee cup calorimeter. So use the same principle now. Pause the video right here and try to solve this problem. So the other device that we can use is what we call a bomb calorimeter. Bomb calorimeter is generally used for explosive substances and gases. So these are materials that have high combustibility. So these are, to find the specific heat of those materials, we use bomb calorimeters. Now let's go into the next one, which is the stoichiometry of thermochemical equations. So a thermochemical equation is a balanced equation that includes the delta H of the reaction. Delta H of the reaction is called as the enthalpy of the reaction. Now the sign of delta H indicates whether the reaction is exothermic or endothermic, whether it releases heat to the surroundings or whether it absorbs heat from the surroundings. Now this magnitude of delta H is generally proportional to the amount of the substance. So the value of delta H can be used to calculate the same way as the mole ratio. So the molar ratio also can be used to calculate the heat as well. So let's take an example here. You have the major source of aluminum. So we have aluminum decomposition, aluminum oxide, so which we require aluminum and oxygen, and it releases an energy of 1676 kilojoule. This is positive, which means here we know that this is an endothermic reaction. Now, if aluminum is produced this way, how many grams of aluminum can form when 1000 kilojoule of heat is transferred? So we have, from this ratio here, for 1 mole of Al2O3, you need 2 moles of aluminum and 3 by 2 moles of oxygen. Now what they are asking you here is that if it is the energy is 1676 kilojoule, so they are asking you how many grams of aluminum can form when you have this much energy. So the energy that they have given is 1000 kilojoule. They want to know aluminum specifically. They want to know how many number of moles. So if 2 moles of aluminum requires 1676 kilojoules of energy, so they have 1000 kilojoules of energy. How much is the number of moles? So again the same principle, cross multiply. So you have 2 times 1000. So let's consider this x is equal to x times 1676. So x becomes 2 times 1000 divided by 1676. So that's 2000 by 1676. So that is 1.19 mole. So the amount of moles is 1.19 mole, but they did not ask you for the number of moles. They asked you for the actual number of grams. So how would you calculate the number of grams here? So we know that the number of moles is mass by molar mass. So to calculate mass, we need number of moles into the molar mass. So the number of moles is given in the question. So from the value we calculate it as 1.19 times we need to know the molar mass of aluminum. Molar mass of aluminum.
The answer I.
So this is 26.98, that is the molar mass of aluminum. So when you multiply both the values, you have 1.19 times 26.98. So that gives you a value of 32.11 grams. So this is 32.11 grams. So next let's talk about Hess's law. Hess's law basically states that the enthalpy change of an overall process is the sum of enthalpy changes of the individual steps in the process. So delta H overall can be calculated as the sum of delta H plus 1 plus delta H2 and so on until delta Hm of the total individual processes that are happening. So how do you calculate the delta H for an overall process is to identify first the target equation and the step whose delta H is unknown. So we manipulate each equation to known delta H values and then target the amount of each substance is on the correct side, and we add the manipulated equations and their resulting delta H values to get the target equation and its delta H. So for example here, let's take this problem here. We have CO plus NO gives CO2 plus half N2. We have two equations that we have here. We have CO plus half O2 becomes CO2 and N2 plus O2 gives 2NO. So first thing that we need to do is we need to make sure that we adjust these equations correctly. So what we do here first is that we know that NO here is only one of them. So the second equation to be manipulated, we multiply half to the second equation. So it becomes half N2 plus half O2. That energy also is divided by half, so it becomes minus 90.3. And we flip the equation. When we flip the equation, remember that this is not the direction in which it is there in the question. This is the direction, so we flip the equation. When you flip the equation, also we flip the sign for the energy as well. So when you add those two equations now, you get the final energy of the delta H of the reaction. So this is one way we calculate the energy of these total reactions using the Hess's law. So these are some standard enthalpy of formation. So standard enthalpy of formation is the energy required to form these substances. So these are that's what is called as the enthalpy of formation. So it's generally represented as delta HF, H degree F. So this here is the representation for standard enthalpy of formation. So they're asking you write the balanced equations to form 1 mole of the following components for their elements in their standard states and include delta HF. So they're asking you for first silver chloride. So first we need to know silver and chlorine. So the silver energy is 0, chlorine it is 121. So add both the values, you get delta HF of minus 127. So remember, the idea here is to make sure that we add both the values. So when you add them, you have to take into consideration both the values. So use the same principle and you can find out all the other examples as well. Now, when you find the reaction here, how would you classify it? First is we take the reactants and we decompose it using negative delta HF. We separate the minus delta HF and we split them into their individual elements, and then finally add the formation of each individual bond's enthalpy to get the final answer for the products. The net difference in energy between the reactants and the products is what we consider as delta H of the reaction. So delta H of the reaction is delta H of the products, delta HF of the products minus delta HF of the reactants. So this is how we can calculate for each individual part here. So let's take the example here. Now always consider that we have to consider M and N as well. M and N represent the coefficients in front of the substances. So here we are talking about 4, 5, 4 and 6. So first energy is we have to find the delta H of the products minus delta H of the reactants. First find each individual part. So for the product part, we need 4 times delta HF of NO plus 6 times delta HF of H2O. So this is the product part minus the reactant part is NH3. So you have 4 times delta HF of NH3 plus 5 times delta HF of O2. So add up the product part, add up the reactant part. So when you can substitute the values from the table, so from this table, use this table and substitute the values. So you will get a final answer of minus 906 kilojoule. So delta H of the reaction. So this is how you can calculate delta H of the reaction. So with that, we end our lecture on thermochemistry. So I'll see you again in the next lecture.